Note in the quadratic formula that the expression inside the radical, this radicand of the quadratic formula, really determines what type of solutions we're going to have. If this is a positive number, then the square root is defined and we get two real solutions. So we name this the discriminant because it helps us to determine what type of solutions we're going to get and how many. The discriminant does not have a square root on it. It's just b squared minus 4ac. It's not the square root of b squared minus 4ac. If this turns out to be a positive number, then we know that we get two real solutions. One using the positive square root, the other using the negative square root. If the discriminant turns out to be 0, then note what your expression really looks like is this, minus b plus or minus the square root of 0 over 2a. Well, the square root of 0 is of course just 0, so it doesn't really matter whether I'm adding 0 or subtracting 0. These both come out to be minus b over 2a. So in this case, we only get one real solution. If that discriminant turns out to be negative, then we'd have something like, for example, negative 1 plus or minus the square root of negative 4 over 2, right? This is a fairly simple example. Then the square root of negative 4 is not a real number. Remember that we can't take the square root of a negative number, and the reason for that is that when we square a number, it turns positive, right? If I take negative 2 and square it, I get positive 4, not negative 4. There's nothing I can do to that 2 or that negative 2 to make the squaring of it come out to be negative. So the square root of a negative number is not a real number, and therefore in this case we get no real solutions. We get what we call imaginary solutions, or non-real, which we'll talk about in another section, but for now we can just recognize that we don't get any real solutions. So it's possible to determine what type of solutions and how many solutions you'll get without actually finding the solutions by just calculating the discriminant. If I look at this first equation, it's not quite ready. I need to get all the terms on one side first. I always like to get a positive leading coefficient, whether I'm calculating the discriminant or I'm going to eventually use the quadratic formula or factor. I really like that positive leading coefficient, so my inclination would be to move that x squared term to the right in order to make it positive, rather than moving the other two terms to the left. It should work either way, though. Now my b squared minus 4ac, I calculate by first identifying a, b, and c. In this case, a is 1, b is negative 2, c is also negative 2. And therefore my discriminant, b squared minus 4ac, is equal to negative 2 squared minus 4 times 1 times negative 2, which is positive 4 minus a negative becomes plus, and that 4 times 1 times 2 is 8, and therefore this discriminant is equal to positive 12. Just the fact that it is positive tells me that this equation has two real solutions. Looking at this next example, A equals 4, B equals negative 20, C equals 25. Again, I can go straight into b squared minus 4ac. The terms are already all on one side in this case. B squared is negative 20 quantity squared minus 4 times 4 times 25. This turns out to be 400 minus 4 times 100 is another 400. So I get a discriminant of 0. Remember that the b squared term is always positive, right? We take the whole number with its sign and square it. So that's always going to be a positive b squared term. And I get that this has one real solution, just because of the fact that the discriminant is equal to 0. I can now carry this idea over to graphs by first identifying the number of real zeros, remembering that the real zeros of a function are the same as the x-intercepts of the graph. So the number of real zeros I'm going to determine by counting the x-intercepts of the graph. In this case, we have 1, 2 real zeros, and therefore I know that this must have a positive discriminant. In the second case, the x-axis is down here. On these images, it's not coming through very clearly, and the graph doesn't cross it at all, so we see that we have no real zeros. If we have no real zeros, then it must be a negative discriminant. The third and final case is where we have a graph that has its vertex on the x-axis, in which case it has only one x-intercept and therefore one real zero. In this case, we know that that discriminant must equal 0. All of these parabolas could have opened up or down, right? In this example here, I could have had a parabola over here opening down. As long as it has only one x-intercept, we know that that discriminant is equal to 0. It could have been over here and opening down, right? Doesn't matter where the parabola is or what direction it's oriented. What we're really looking at is how many x-intercepts it has, how many times it crosses that x-axis.